Okay, so I'm going to bring up the lecture notes section, and this is the section 8.1 set of notes. All right, so first thing we're going to do is we're going to take a look at some basic terminology. All right, and as far as basic terminology is concerned, we just have two distinct points between A and B. That's called a line. So a line is written out. Notice that there are two distinct points. The arrowheads indicate that the line extends forever in both directions. Next, we have a line segment, and notice that a line segment has two endpoints. Okay, so a line segment doesn't extend forever in either direction. And then notice lastly we have a ray. So a ray has one endpoint and extends forever in the other direction. Note that when you write out a ray, you must denote the ray starting with its endpoint. So notice that this is called ray AB. We cannot call it ray BA because B is not the endpoint. All right, so we must start our ray notation with the endpoint. Now, next we have what are called angles. Now, an angle is just two rays that meet at a point, and that point is called the vertex. Right? So when we're kind of writing out angles, there are a couple of ways that we can actually write out an angle. And I'm going to go to OneNote for just a second. And so when we write out angles, all right, so notice here I'm giving an angle, and I'm going to call this A, B, C. All right, so just notice that we have ray BA and we have ray BC. They're joined together at point B, which is called the vertex. So I can call this either angle B, right? I can call it by its vertex alone. So notice this funny looking L, that's the mathematical symbol for angle. I can also call this angle ABC. I can also call it angle CBA. All right, so I can actually label this out by its vertex alone, or if I label it by its sides, I must have the vertex as the middle coordinate. Okay. Sometimes you may see a number inside of our angle. I could also call this angle 1. All right, angle 1. All right, next we're going to talk about positive angles and negative angles. Now, all of our angles are considered to be in an XY coordinate system. So I'm going to just kind of review the XY coordinate system. So in the Cartesian coordinate system or the XY coordinate system, we have the x-axis as our horizontal axis, and we have our vertical axis as our y-axis. These two axes meet at a point, and that point is called the origin. Right? The origin has a coordinate 0, 0. All right, the two axes also split our plane up into 4 different regions. We call these quadrants. So the top right quadrant, that's Q1. The next quadrant over is Q2. We have the bottom leftmost as quadrant 3. and we have the bottom rightmost quadrant as quadrant 4. Right. All right. So just give me a second. I'm going to kind of erase all of this for just a second. Okay, give me 1 second. I'm going to close this down and just bring it back up. All right, so all of our angles are understood to be in what's called standard position. So now for each one of our angles, we have a starting ray or an initial ray or an initial side, and we have a terminal side. All right, so standard position means that our initial side must start along this positive x-axis. The terminal side can either be rotated counterclockwise or it could be rotated clockwise. Normally, you're going to see an arrow which indicates which way the terminal side was rotated. So in this case, if the terminal side is rotated counterclockwise, we have what are called positive angles. So we have an angle of positive 120 degrees. When we talk about negative angles, our terminal side is rotated clockwise. So here's what I mean. So all of our angles, they're in standard position, so they start along the positive x-axis. However, if our terminal side is rotated rotated clockwise, this gives us a negative angle. So I'm going to estimate this at negative 120 degrees. So notice that the arrowhead is rotating in a clockwise manner. That indicates a negative angle. So now, one other caveat when you talk about negative and positive angles are our angle measures. So if you're dealing with a positive angle, right, this is how you can label your degrees on your axes. So here I have 0 degrees. Here I have 90 degrees. Okay, here I have 0 degrees. Here is 90 degrees, 180 degrees, 270 degrees, and then we have 360 degrees, right, for one complete rotation. If, however, you're looking at negative angles, and here are our degree measures for all negative angles. Here we have 0 degrees. Notice at the bottom we have negative 90 degrees. Then we have negative 180 degrees. Next, we have negative 270 degrees. And then we have one complete rotation at negative 360 degrees. So I want you to notice here that when we graphed 120 degrees, it was in quadrant number 2, right? When we graph negative 120 degrees, notice that that angle is in quadrant 3. So we must be careful when we're plotting positive angles and when we're plotting negative angles. All right. So here we have an example of a positive angle. So just notice that it was rotated counterclockwise as indicated by the arrow. And notice here we have a negative angle in which the terminal side was rotated clockwise. Now, I will skip through some of the slides as they're not pertinent to our course, but here's just some background information about degree measure. And it was developed by the Babylons about 4,000 years ago. If you divide the circumference of a circle into 360 parts, notice that that's approximately the number of days in a year. There are exactly 360 degrees in one rotation or one revolution. An acute angle is an angle between 0 and 90 degrees. A right angle is an angle that is exactly 90 degrees. Normally, when you see your right angles, all right angles will be accompanied by a box that you'll see, and that's the mathematical symbol for 90 degrees. Right? So without the box, I wouldn't necessarily assume that it's a 90-degree angle. Next, we have an obtuse angle, which is an angle greater than 90 but less than 180 degrees. And lastly, we have a straight angle, which is exactly 180 degrees. All right, now we don't really deal too much with supplementary and complementary angles. We also don't deal with degrees, minutes, and seconds, right, or decimal degrees. All right, but we will take a look at coterminal angles. And we're also going to take a look at radian measure. Okay, but before we take a look at coterminal angles, we're going to take a look at radian measure. I'm also going to bring up, I'm going to go back to the main page of the course. I'm going to go into the formula sheet section, and I'm going to bring up the unit circle. And I want to talk more about the unit circle and about radians. Okay, now here we have what is called a unit circle. And this unit circle, it has an equation, x squared plus y squared is equal to 1. And in this unit circle, the radius, so keep in mind that the radius is the distance from the center to the outer rim of your circle. The radius is 1. Now, one thing about the number 1 is arbitrary, which means that you can actually scale anything to a unit of 1, okay, which makes the trigonometric functions work for no matter how big your radius is. For example, 10 feet can actually equal to 1 unit. Right? So in this unit circle, the radius is 1. It didn't say that it has to be 1 feet or 1 mile or 1 centimeter. It just has to be 1 unit. So we can arbitrarily scale anything to a 1. We can make 3 feet equal to 1 unit. Okay, so that's what drives the unit circle and the trig functions as being representative of all circles. All right, so in this unit circle, the radius is 1. Now you're going to notice a couple of things on this unit circle. You notice the degree measures, right? For example, and I can't actually write on this slide, but let's say we have our first angle and it starts at the positive x-axis, so we would have a initial side at 0. And then let's say for 30 degrees, we would have a terminal side at 30 degrees. Notice that 30 degrees is written as pi over 6 radians. So notice, first off, that on this unit circle, there are some degree and radian equivalents, right? 30 degrees is pi over 6 radians. 45 degrees is pi over 4 radians. 60 degrees is pi over 3 radians. 90 degrees is pi over 2 radians, so on and so forth. Okay. So first off, I want you to notice that there are some degree measure to radian measure conversions. Okay, we're going to see in a second how we can calculate these things manually. The next thing you'll notice on the unit circle are the ordered pairs. For example, 30 degrees, which is pi over 6 radians, it has the coordinates of square root of 3 divided by 2, comma 1/2. So what does that mean? Well, that means that if we were to plot out 30 degrees, right, in a x and y axis system, since the radius is 1, in order to plot 30 degrees, we would go over a distance of square root of 3 over 2 on the x-axis, and then we would go up to 1/2, right, which would give us this plot on our circle. Right through this point lies our terminal side, and that terminal side gives us a measure of 30 degrees or pi over 6 radians. Notice that there are a set of ordered pairs for every degree measure. All right, now before we actually get into what the numbers, the ordered pairs actually mean, we're going to talk about how to convert from degrees to radians and from radians to degrees. All right, so I'm going to go back to our 8.1 set of notes. Right, and we have this somewhat awkward definition. So the definition says that an angle, so if we look to the right, we see we have an angle. We have an initial side that starts along the positive x-axis. We have a terminal side. This thing is rotated counterclockwise, so we know it's some kind of positive angle. The symbol that you see, okay, the circle with like the line through it, this is called theta. And as we go through the trig course, just as in the algebra course, we have variables. In the algebra course, the variables were the Arabic lettering system, right? X, Y, Z. In trig, our variables are written out as Greek letters of the alphabet. So we'll be looking at things such as theta, right? So this is the Greek letter for theta. We're also going to look at beta. We're going to look at alpha, gamma. Any variable in trig will be written as a Greek letter of the alphabet. So in this case, this is theta, and theta simply means an unknown angle measure. Right? So we have what's called theta, which is our central angle measure. And notice we have r, which is our radius, right? The radius goes from the center to the outer rim. And then notice we have s. S is called the arc length, or the length of arc between our angle measure. But for now, we're kind of concentrating simply on radian measure. So it says that an angle with its vertex at the center of a circle that intercepts an arc on the circle equal in length to the radius of the circle has a measure of 1 radian. So that means that if your radius, right, and if I were to put a ruler to my radius, and if I were to measure from here to the outer rim of my circle, I would get some measurement. If I take the same ruler and if I measure my arc length, if these two have the same length, right, they're equal in length, then the measure of my angle is 1 radian. Okay, so now what does all this mean? Now, 1 radian actually has a value. So this is how that value is determined. It says that the circumference of a circle is given by C is equal to 2 times pi times r. So recall that the circumference is the distance around a circle, and that's equal to 2 times pi times r, where r is the radius of the circle. It shows that 360 degrees, right, which is the distance around a circle, it has a measure of 2 pi radians. Right? So I'm going to go back to OneNote for just a second. So 360 degrees is equal to 2 pi radians. Right. I'm going to solve this for radians. I'm actually going to treat it as an algebraic expression. So I'm going to divide both sides by 2 pi. So if I were to divide this up, 360 degrees divided by 2 pi. Notice I get about 57.3 degrees. That's equal to 1 radian. Now I want you to understand that this radian is an understood value. So here's what I mean by it's an understood value. If I were to go back to the unit circle, right, and I'm going to put in pi over 6. So I'm going to put in pi over 6. And notice I don't actually get 30 degrees. I get 0.52. But notice that radian is understood to be 57.3 degrees. So this thing is read as pi over 6 radians. Now you're going to hear me sometimes say this is pi over 6, but in actuality it's pi over 6 radians because radian carries the 57.3 degree. So in essence, if I were to take pi over 6, and if I were to multiply that by 57.3 degrees, so notice I am rounding a little bit, so I do get rounding error. Now notice that I get 30 degrees, right? So I want you to know that when you're reading this unit circle, when you're converting from degree to radians, notice that pi over 4 radians, that radians actually carries 57.3 degrees to make the two things equal. Okay. All right, so let's take a look at some examples. All right, so here we're asked to convert between degree and radians. We're given 9 pi over 4, and we're asked to convert from radian to degree. We're also asked to convert 45 degrees from degrees to radians. All right, so here is the math on how to do so. If we want to convert from radian to degree, we simply multiply by 180 degrees divided by pi. In order to convert from degree to radian, we multiply by pi over 180. All right, so let's take a look at an example. So here is the examples from the slide. We're asked to convert to degree 9 pi over 4. Well, if I'm asked to convert from radian to degree or to degree to radian, the first place I would look is on the unit circle. So I'm going to look at the unit circle, and I'm going to see if there's a conversion from 9 pi over 4 to 4. All right, so taking a look back at the unit circle, right, I see that there's a pi over 4, there's a 3 pi over 4, there's a 5 pi over 4 and a 7 pi over 4, but not a 9 pi over 4. Right? So I'm going to multiply by 180 over pi. Right? Because I'm converting from a radian to a degree. So notice when we convert, we can actually cross cancel. Notice that the pi's will cancel. I can actually reduce 180 and 4. I can divide both of those things by 4. 4 divided by 4 is 1. 180 divided by 4 is 45. And next I can multiply 9 times 45, which would give us 405 degrees. So 9 pi over 4 radians is equal to 405 degrees. All right, next we'll convert to radians. All right, we're given 45 degrees and we're asked to convert to radian. Right, so here again, the first place I'm going to look is the unit circle. So notice that we do have a conversion. 45 degrees is pi over 4 radians. Right, but if we actually do the math on that, we would take 45 degrees and we would multiply by pi over 180 degrees. We can divide 45 and 180 by 45, so that gives us a 1 and a 4. So we have pi over 4 radians. All right, so at this time, I have a couple for you to do. So I want you to convert, and I don't know why my pen is so dark now. Convert to degree. Five pi over 6. I would like you to convert that to a degree. And I would like you to convert to radian negative 150 degrees. All right, so at this time, I'm going to pause the recording. I'm going to give you a second or two to complete the two problems, and then we'll come back with the solution. All right, so we're turning back with the solution for 5 pi over 6. Converting that to a degree measure, I'm going to look at the unit circle. All right, so if I look at the unit circle, I can see that 5 pi over 6 is 150 degrees. All right, but in order to calculate that k by hand, we're going to take 5 pi over 6. We're going to multiply that by 180 over pi. So our pi's are going to cancel. We can reduce 6 and 180. We can divide both of those by 6. So 6 divided by 6 is 1. 180 divided by 6 is 30 degrees. So if we multiply across, we have 150 degrees. All right, next we're asked to convert negative 150 to the radian measure. So we have negative 150. We're going to multiply by pi over 180. right? So here again, we can reduce, right? We can divide both 150 and 180 by 30, right? So notice this is still negative. So that reduces to a 5 and a 6. So we have negative 5 pi over 6 radians. All right, I'm going to go back to the lecture notes. All right, and I'm actually going to backtrack. We're going to talk about coterminal angles. All right, so on the slide, it talks about coterminal angles, and it starts off with what are called quadrantal angles. Okay, and quadrantal angles are angles that are not in quadrants, they're between quadrants, right? So if we take a look at the unit circle, the quadrantal angles would be 0 degrees, right? Because 0 degrees is not in the first quadrant, it's not in the fourth quadrant, it's between quadrants. So that's a quadrantal angle. We have 90 degrees as a quadrantal angle, 180, 270, and one complete rotation, 360. We also have negative 90 degrees as a quadrantal angle, negative 180, negative 270, negative 360. Those are also considered to be quadrantal angles. We talked about positive, we talked about standard position, right? For angles in standard position, their initial side must start along the positive x-axis, and the terminal side is, okay, can either be rotated counterclockwise or clockwise. Here is the definition of a coterminal angle. Coterminal angles start in the same spot, they end in the same spot. The only difference is the number of revolutions that the terminal side makes. Okay. Let's look at an example. All right, so in the slide it says, well, I actually go to OneNote. Okay, and I believe there is a way to make my pen a little bit darker. I don't know why it lightened up. Okay, I will have to figure that out later. Okay, I think that did it. All right, so we're going to talk about coterminal angles. Okay, and we're going to start off with a 60-degree angle, right? So this is my initial side, and this is my terminal side, and we're going to say that this is 60 degrees, right? And this thing is being rotated counterclockwise, right? So we have 60 degrees. So now remember that coterminal angles, they start in the same spot and they end in the same spot. So let's just say we take this terminal side and we rotate it 360 more degrees, right? Which brings us back at the same spot. So if we were to add 360 degrees to 60 degrees, we get 420 degrees. Right? So the 60-degree angle and the 420-degree angle, they both start at the same spot, they end at the same spot. The difference is the number of revolutions. Right? We can add 360 again, right? If we were to add another 360 degrees, right? So notice now we have 3 revolutions. So if we were to add 360 to 420, we get 780 degrees. Right? So all three of these angles are coterminal angles. And keep in mind that this will keep on going. You could also subtract 360 degrees. So for example, right? So here we have 60 degrees. So let's say in this case, we want to subtract 360 degrees. So we're going to rotate. Okay. So we're going to rotate clockwise. So if we were to subtract 360 degrees from 60 degrees, notice that we get negative 300 degrees. Right, so just keep in mind our scale. Here we have, since we're talking about negative angles, right, this is 0 degrees, negative 90 degrees, negative 180, negative 270, and negative 360. Right, so keep in mind that a negative 300 degree angle would lie in the first quadrant. So you can add as well as subtract 360 degrees. All right, so let's look at an example. So we're asked to find the smallest possible positive measure for a coterminal angle for each one of these angles. So we have a 908 degree angle, and we have a negative 75 degree angle. So first we're going to start with a 908 degree angle, and I'm actually going to sketch out a 908 degree angle. All right, so which quadrant does that angle lie in? Find an angle between 0 degrees and 360 degrees. So I'm kind of rewording. So where they say the smallest possible positive angle, that would be an angle between 0 and 360 degrees. That is coterminal to 908 degrees. All right, so I'm going to just sketch out a 908 degree angle. All right, so it's in standard position, so it starts along the positive x-axis. So let's just say we rotate it one time, that's 360. Right, we're going to rotate it 2 complete revolutions, right, and that's 720. Now, if I rotate it a third time, I would get 1080, which exceeds the 908. So from this point, I'm going to go in quadrant increments. All right, so here we have 720. So if I add 90 to 720, this would be 810 degrees, right? So I'm going to keep on going a little bit. If I add 90 to 810, we have 900 degrees, All right, so I'm going to keep going a little bit. So a 908-degree angle should lie in the third quadrant. All right. So now in order to find the smallest possible positive coterminal angle, we're simply going to unwind it or subtract 360 until we get a value between 0 and 360. All right, so if I were to take 908 degrees and subtract 360, I believe I get 540 degrees. I'm going to subtract 360 more, and we get 188 degrees. Right. So 188 degrees is coterminal to 908 degrees. Right, so it's simply a matter of adding or subtracting 360. All right. There's one more. We're asked to also find the smallest possible positive measure coterminal angle with 75 degrees or negative 75 degrees. All right, so I'm going to sketch out negative 75 degrees. All right, so keep in mind, since we're dealing with a negative angle, we have 0, negative 90, negative 180, negative 270, and one complete revolution back at negative 360. All right, so we're going to have it in standard position. Negative 75 degrees would lie in the fourth quadrant. Right, so in order to find the smallest possible positive angle, here we're going to add 360. So if we have negative 75 degrees plus 360 degrees, that gives us positive 285 degrees, which means that the negative 75 degree angle and the 285 degree angle are coterminal angles. So now I'm going to give you a couple of problems to do. All right, so the directions are the same. All right, find a angle between 0 and 360. That is coterminal to 1080 degrees. And for B, find an angle between 0 and 2 pi. That is coterminal to negative 15 over 4 pi. All right, so I want you to answer these two questions. I'm going to pause the video and we'll return with the solution. All right, we're going to return with the solution. So first we're asked to find an angle between, let's see, there was a question. Okay, those were the answers. Okay. All right, so first we're going to find an angle that's between 0 and 360 degrees. Okay, so that should be the smallest one. So we're actually going to, if we were to sketch out 1080, right? So this is 0, 90, 180, 270, and 360, right? So it begins and along the positive x-axis. So we rotated one complete time, that's 360. We rotated two times, that's 720. We rotated three complete times, that's 1080, right? So now if we were to subtract, so since we want the smallest, I'll just do this on the calculator just to save some time. All right, so we have 1080. We're going to subtract 360, subtract 360. Since we want the smallest here would actually be 0, okay? Because in our directions is between 0 and 360. So even though we have 360, 0 would be the smallest. All right, so here we would have 1080 and 0, our coterminal. All right, now for this one, now even though an example, I didn't talk about actually converting one from radian, okay? So the first thing I'm going to do here is I'm actually going to add 360 degrees until I get something positive. But the 360 degrees I have to add to this must be 2 pi. So I'm going to take negative 15 over 4 pi, and we're going to add 2 pi. All right. So I'm going to convert 2 pi to a fraction. And then I'm going to make equivalent fractions. So I have a 4 in one denominator and a 1 in another denominator. So the common denominator between 1 and 4 is 4. All right, now I must make equivalent fractions. So for this first denominator, the 4 was multiplied by 1, right, to get 4. If I multiply the top by 4, right, excuse me, by 1, that numerator stays the same. For the second fraction, that 1 was multiplied by 4. To get the common denominator, we multiply the top by 4, so we have 8 pi. And when we subtract fractions, we can keep the common denominator, combine the numerators. Right, so I get negative 7 pi over 4. All right, so once I added 360 degrees, which is 2 pi radians, I get negative 7 pi over 4. Now I'm going to add 2 more pi, right, or 360 more degrees. So I have negative 7 pi over 4 plus 2 pi, right? And I'm going to write 2 pi as a fraction. So here again, I have to find a common denominator, which is 4. All right, for my first fraction, it stays the same. For my second fraction, that 1 was multiplied by 4 to give us the least common denominator. We multiply the top by 4. So now we keep our common denominator. We combine the numerator. And we have pi over 4 as a result. All right, now this is one way to do it, right? We can actually subtract 2 pi, right, until we get something positive. Now, here's another way you can do it. We can actually, and this is one thing about the answers. If you're given an answer, or if you're given the question in a degree measure, then you must write the answer out as a degree. Okay, I'm trying to shrink the screen. So like for our first one, we were given 1080 degrees, so we answered the question in degrees. For the second problem, we're given the question in radians, so we must answer the question in radians. All right, so the angle that is coterminal with negative 15 pi over 4 would be pi over 4. Right, now here's another way we can do the problem. We can actually take negative 15 pi over 4 and we can convert it to degree measure. So now one thing I want you to see when you quickly convert a radian to a degree, okay, you can multiply, by the 180 over pi, and convert. But here's an easier way to convert. If I go back to the unit circle, and here's what I want you to notice. If you look at the left-hand side of the unit circle, pi is actually equal to 180 degrees, right? So 180 degrees is pi. So if I wanted to convert negative 15 pi over 4 to degree measure, I can simply take negative 15. I can multiply that by pi, and pi is equal to 180 as a degree measure. And I can divide by 4, right? And I get negative 675 degrees, right? So if I were to sketch out negative 675 degrees, right, this is 0, negative 90, negative 180, negative 270, and negative 360. Right, so if we were to sketch out negative 675 degrees, which is negative 15 pi over 4, right, we will make one complete revolution. Now, if I make two complete revolutions, that will put me at negative 720, right, which overshoots our negative 675. So now we'll go by 90 degree increments. So if we were to add negative 90 degrees to negative 360, we get negative 450. Right. If we add 90 degrees to negative 450, we get negative 540. Right. So we haven't quite reached 675 yet. If we add negative 90 degrees to negative 540, we get negative 630. So that negative 675 should put us somewhere in the first quadrant. So if we were to take negative 675 and then we were to add 360, right? If I add 360, I get negative 315. If I add 360 again, I get 45 degrees. From this point, I would convert 45 degrees to radians, right, which would give me pi over 4. All right, but notice I must still answer the question as a radian measure. All right, so a couple of ways to do that particular problem. Okay, now the last thing we'll take a look at is arc length. All right, so here we have the PowerPoint slide on arc length, and it states that the length S of an arc intercepted on a circle of radius r by a central angle of measure theta. So here again, that's the Greek alphabet for theta. Radians is given by the product of the radius and the radian measure of an angle. Right, which is this formula. S is equal to R times theta, where theta has to be in radians. Right, so the angle measure that you're given has to be in radians. All right, so I'm actually going to map this out. All right, so when we talk about arc length, right, here's our setup. We have a circle, right, and on that circle we have a center, and the distance from the center to the outer rim of the circle, that's our radius. Right, so here we have a distance from the center to the outside rim of the circle, that's our radius. And also our radius is here, also on this ray. Notice that the area between the rays, this is our arc length, which is S. All right, so S is the arc length. Okay, and we have a central angle, which is theta. All right, so we have the formula. S is equal to R times theta, and theta has to be in radians. Now, just one thing about this formula. This is an algebraic formula, so it can be manipulated. So from this formula, we can derive two other formulas. We can derive the formula that R is equal to S divided by theta. Right, so if you're asked to find the radius, if you're given the arc length and the central angle measure in radians, you can find the radius. We can also derive the formula theta is equal to S times R. Right, so if you're trying to find the measure of the central angle, you can simply divide the arc length by the radius. All right, so for our example, we're given a circle that has a radius of 25 and an arc length, an essential angle measure of 45 degrees. All right, well, we're going to use the formula S is equal to R times theta, but in order to use the formula, theta has to be in radian. Right, so S is equal to R, which is 25, times our central angle measure, which is 45 degrees, right? So from a previous calculation, we calculated that 45 degrees is pi over 4 radians. Okay, and from this point, there are two versions of the answer. We have something that's called the exact value, and there's something called the approximate value. Okay. Now, here's the difference in the two. For the exact value, I must leave pi as pi, right? Because pi is an irrational number, and the irrational numbers, they never stop and they never repeat. So it's impossible to write it out exactly other than symbolizing it. All right, so I'm going to take 25, I'm going to divide that by 4. So the exact value is 6.25 pi, and our unit was inches. Right, so that is the exact value. So notice in the exact value, we must leave pi as pi. Right, now here's the approximate value. So for the approximate value, I'm going to take 25, divide that by 4, but this time I'm going to multiply by pi, and this is the approximate answer, 19.63 inches. Okay, so it'll be more specific in the instructions on which place value you are to round. All right, so we get 19.63 inches as the approximate value. All right, so with that being said, I'm going to go back to the main screen. All right, I'm going to stop the recording.